I'm going to talk a lot about this handout that I posted on Moodle. Those of you at home, you want to make sure you have this in front of you. It's titled The Distribution of Sample Means and Probability. I brought extras for those of you here. If you all have it, anyone want one? Need one? Okay, I think it'll be helpful. What's that?
I realized there was one perhaps.
Oh, okay. Yeah. Okay, so we're going to jump in and start talking about inferential statistics. That's really what we're going to focus on. We're going to focus on inferential statistics for the most part for the entire rest of the semester. Inferential statistics, they're a class of statistics and they all have a similar goal. The goal is to determine whether we can legitimately extend our findings from a sample to the population. Can we claim that what we found in the sample is a real effect, that it would be found, across different samples? And that's always the goal of research. We're not interested in doing this big elaborate study just so that we can make statements about the 100 people that were in our study. We're trying to figure out whether or not the trend that we saw was representative of what actually happens in the population. Before jumping into that too much, I wanted to just remind y'all of this term, sampling error. This becomes very important in inferential statistics. I introduced you to that term earlier in the semester, and you probably encountered it before. All right, so sampling error is a discrepancy between a population parameter and the corresponding sample statistic. So whenever I have a population, like if I had a population of students in my class, and there is a population parameter, say the percentage of correct on the exam. Right? So there's some number that exists. And that's actually something I could find quite easily, right? But I could take a sample, let's say 15 students from the class. The class has about 32, 34 people. If I was to take a sample of 15 people from that population and compute the mean from just that sample, the mean would probably be pretty close to the population mean, right? Be pretty close to the average class that actually exists in my 221 class, but it wouldn't be exact, right? That would be really odd. I expect there to be some discrepancy there, right? And there would probably be quite a bit because I only have 15 people in my sample, right? So we always expect there to be some sort of discrepancy between a sample mean and the population mean from which the sample was drawn. Okay, I'm going to work with a particular example where the dependent variable is going to be IQ score. Let's say that in the population, we know that the mean is 100. And the standard deviation is 10. I'm going to start with that knowledge about the population. Okay, and then I decide to conduct a study where my independent variable is going to be diet. So I want to see if diet impacts IQ. So I'm going to take 50 people. I'm going to randomly select them from the population. These are adults. It's adults in America. That will be my population. So that's what these stats refer to, adults in America. I'm going to take a random sample of 50 adults from this population. Oh, I'm sorry. I changed my ID on you. My ID is actually a drug. I'm sorry. I apologize for that. So no diet. That's too messy. It's hard to follow around people and make sure they're eating a correct diet. So I'm going to do a drug. I've developed a drug, and I think it impacts IQ. And of course, if it does, maybe I can market it and make lots of money, right? Okay. So I want to try and find out whether or not my drug actually does impact IQ. So same idea. I take 50 people from the general population, and I give them my drug for 6 months. So I give them my drug for 6 months, and then I take the mean, right? I'm going to start seeing that symbol a lot. You're going to see that symbol and that symbol. They both mean mean, but that X with the bar over it means the mean of a sample, right? And let's say that it comes out to be 106. So the sample mean is 106. Okay, so the purpose of doing this study was to try and gain evidence showing whether or not the drug impacts IQ. And one thing we can see is that there is a discrepancy, right? My sample of 50 people, their IQ is 6 points above the population from which they're drawn. So it looks kind of like the drug has an effect, right? It would be a mistake to immediately assume that it does, though, right? Why? Well, because sampling error, right? It could be that I just happen to get a sample of 50 people that are just that discrepant from the population mean. That it could be that I just took 50 people and didn't do anything to them, and I measured their IQ and it could have been 106, right? You expect there to be some discrepancies in your samples compared to the population, right? So that is what we use inferential statistics for. And if it wasn't for inferential statistics, we would never be able to get a grasp on any of this, right? So they're very useful, especially when you're dealing with people where there's so much variability in the dependent variable, where we expect the sample means to fluctuate quite a bit. Okay, so yeah, that's a purpose, is to try and determine, well, is this actually evidence that there's an effect? Right now, we don't have that yet. Okay, so we use inferential statistics. Inferential statistics is using, we estimate what is the likelihood of getting an outcome like this. So we're going to use the laws of probability and the data, obviously, that we obtain. We use those two things to estimate the likelihood that the result that we've got was just due to chance, just due to sampling error. And estimate that likelihood. If that likelihood is very low, so if it's very unlikely that that 6 point difference, maybe it's so wide, so big, it's very unlikely that it's due just to sampling error. It's only in that circumstance that I can then claim that there is an effect of the drug. And so the whole purpose of inferential statistics is trying to estimate what is the likelihood of getting this particular outcome. And if that likelihood is only if it's very low, that it was due to sampling error, am I able to make a conclusion that there's likely an effect? Okay. So all of inferential statistics is really going to come down to two sort of main steps. And the details changed, quite a bit when you go from one type of test to another. We're going to learn about ANOVA test, F test, single sample t-test, z-test. We're going to learn a lot of different inferential tests. They all have their little niche depending on what kind of methodology you've used or what kind of data you've collected. But it always comes down to these two major steps. So the first thing that we do is we try to kind of determine what kind of outcomes we would expect based on chance alone. Another way to say that is sampling error. And so the first thing we do in all these types of tests we're going to learn about is we determine, well, what kind of outcomes would we expect to occur? Just based on sampling error. It's based on chance. What kind of outcomes would I expect to occur just based on sampling error alone? What would the sample means kind of look like if I was to draw, samples from a population which the mean is 100 and the standard deviation is 10? If I was to just take a random sample of, say, 50 people and compute the mean, not do anything to them, how far off would I expect that sample mean to be from the population mean? So that's kind of the first thing I do. And again, the details will differ, but it's always this. This is one of the main things we do first. What kind of outcomes would we expect to occur based on sampling error alone? And then the second thing we do is compare the outcome in our study the outcomes expected by chance. So the second thing we do is compare the outcome of our particular study to the outcomes that we'd expect based on sampling error alone, right? Based on chance. And so again, first thing we do, what kind of outcomes would we expect? What would we expect in this case? What kind of sample means would we expect? Would we, of course, we'd expect the sample means if we're drawing them from that population to be around 100, right? But you're going to have some discrepancies there. So what kind of outcomes would you expect that's just due to sampling error, no effect of anything else? And then once we know what that is, then we compare the outcome of our particular study. And the detail, in this particular case is this. Later it'll be something else. In this case, the outcome is a single sample mean. So we compare the outcome in our study to the outcomes expected by sampling error alone. And if the outcome that we had got does not fit into the expectations, right, does not align with what kind of outcomes we'd expect by sampling error alone, that is where we then have evidence that there's an effect. Because you can't just easily attribute it to what you'd expect based on sampling error alone. All right, so again, it's good to kind of keep this is like the forest. And it's good to keep a big perspective because it kind of helps it fit everything else in. As we go through the semester, we're going to get into kind of some nitty-gritty details, right? But it always is helpful to kind of think about what we're doing and why. And what we're doing and why is this. We're trying to figure out, do we have legitimate reason to conclude that our effect is real? In this case, that the drug actually affected IQ. Because based solely on this, we don't yet. We have to go through a process. We have to figure out what kind of outcomes would we expect based on sampling error alone, and then compare our outcome to those expectations. And if what we found is really doesn't align with what those outcomes would be based on sampling error alone, that's where you have evidence that there's something more driving the difference than simply just sampling error. And of course, maybe I'll keep that up there. That's all very mysterious, like how can we possibly do any of this stuff? Right? How do we know what kind of outcomes would we expect, right? That's what we're going to talk about today. So we're going to kind of focus on this one major part. Maybe we'll get down to here if we have time. So again, the goal, we're trying to figure out whether or not that 6-point difference, whether that is simply just sampling error or whether it might be due to an effect of the drug. So first we have to figure out what kind of outcomes would we expect? Right? Based on, we know this population, we know the population mean is 100 and the standard deviation is 10, right? Well, what kind of outcomes would we expect from a sample of this size, right? We have a relatively small sample. So that's why we use something called the distribution of sample means. I'm not going to test you on this part, but it's a type of what's called a sampling distribution. And there's all kinds depending on the nature of your study, the details of your study, the methodology of your study. The most simple one, the first one we learn about, is the distribution of sample means. And this is going to speak to that one first part. What kind of outcomes would we expect to occur just based on sampling error alone? And we do that. That's what this will be, the sampling distribution of means. Will tell us what kind of outcomes we'd expect by sampling error alone. There's several things about this distribution. It is a theoretical distribution. It can be empirically verified, but it's theoretical, meaning we don't actually have to construct it painstakingly by drawing 1 million samples from the population. We can mathematically prove it. We can prove it also empirically. We don't need to. It's a lot of work to do that. But okay, so it's a theoretical distribution. It's kind of like a what if, right? What if this would happen? And what it represents is the distribution of sample means. It tells us what kind of outcomes or sample means we'd expect based on chance. So that is, it's what I just talked about. It tells us what kind of sample means we'd expect to draw from samples of regular people, in this case, who do not take the treatment, do not have that drug. And the definition is, it's a theoretical, as I mentioned, a theoretical distribution. It represents the collection of sample means of all possible random samples of a particular size, the size matters, as you'll later see, that can be obtained from the population. So the definition of the sampling, the distribution of sample means, it represents the collection of all sample means. Collection of sample means of all possible random samples of a particular size that can be obtained from the population. And so it represents the collection of sample means of all possible random samples of a particular size that can be obtained from the population. And to kind of imagine, kind of wrap your brain around the distribution of sample means, what you can do is just imagine repeatedly, so this is our population. And in this case, this is our population. So it's this distribution of sample means depends on what your dependent variable is, right? In this case, this is my dependent variable. The mean is 100, is IQ, and the standard deviation is 10. So we can imagine taking an infinite number of random samples. Start with sample number 1, right? So just taking a sample from this population of that size of 50 individuals. And size matters because it turns out that the larger the sample size, the larger number of people in your sample, the less error there is. The closer that sample mean will approximate the population mean, in this case of 100, right? So because we're drawing a sample from that population, it's kind of anchored to that population. So the sample mean will typically be pretty close to that population mean. Right? It's the anchor, we're drawing from that particular population. So we can imagine doing that. Again, just as an exercise to help us understand what this distribution sample means is. So imagine that we did that. So let's say for the first sample mean, again, we don't actually need to do this because there are known properties of this distribution, but it's just to try and make us understand what it is. So you can imagine if I was to take the first sample, my first of many random samples from the population, this population, and I take those in 50 individuals, so that's my sample size, and I compute the mean. And just say, let's say the first time I compute the mean from the first sample, it's 102. That's reasonable, right? And then I put those 50 people back in the population. I take another random sample of 50 individuals from the population, give them an IQ test, and compute the mean. And again, I'm not interested in any effect they drug right now. I'm trying just to establish what kind of outcomes would occur just based on sampling error. Right? So let's say the second group was 99. The mean IQ was 99. I take another group, third group from the population of 50 people, compute the mean, it was 100.5. Ooh, that was very close to the population mean. That's going to happen sometimes. I take my fourth sample from that population and compute the mean, and now let's just say it's 97.5, so it's 2.5 points, IQ points away from the population mean. Well, that's going to happen sometimes, right? Most of the means will be really close, closest to the population mean, and as you get farther out from the mean of 100, the sample means the frequency of those sample means being very far discrepant will become smaller and smaller. There'll be fewer and fewer of them. And you can imagine just keep doing this. The fifth sample mean, say it was 104. And again, do this an infinite number of times, right? So they just a big long line of data, right? With all the samples and then the value for the sample means. Okay, and that is the distribution of sample means. That's the kind of outcomes we'd expect based on sampling error alone. And that there's some important properties of this distribution. And that makes it very useful to us. The first property of the distribution of sample means is that as long as the sample size is not very small, as long as it's greater than 29, so assuming you have decent sized samples, then the distribution is normally distributed. So one way to kind of think about it, these sample means, right, they represent means, but we can treat them just like any variable we've dealt with in the past, right? So we can take these data and we can put them in a table, we can graph them. Okay, in fact, I did that on the bottom of this page as a graph. And instead of representing individual scores, they represent sample means, right? So every entry into that graph represents the mean of 50 individuals, a sample mean. So the distribution is normal in shape, as long as you've got decent sized samples. It's all that we learned about the normal distribution is applicable here. That's very handy. Okay, another thing that we can do, that we learned how to do with normal scores, that we can deal with this as well, is we can compute the mean of this distribution. So we're getting a little crazy because we're talking about means of means, but we can do that. We can take the mean of the distribution of sample means, right? Because we're treating these just like regular scores, right? So we can add them up, add up all those sample means, the infinite number of sample means, and divide by n. And when we do that, this is one of the properties, when we do that, the mean of the distribution of sample means turns out to be exactly equal to the population mean. So that's a second really important property. Mean of the sample, mean of the distribution of sample means is equal to the population mean. So this is the second really important quality of the distribution of sample means, is when we know what the mean of that distribution will be. It's equal to the population mean. And it kind of makes sense if you stop and think about what's going on, right? We are taking an infinite number of samples from that population. That population's our anchor, and we're computing the mean of each sample. And it makes sense that if we're just taking random samples and we're doing it an infinite number of times, that half the time, right, the sample mean will be higher than the population mean in value. It will just happen to be a little higher, or quite a bit higher. Most of the time, just a little bit higher. That's going to happen. But it's just as likely, just as often, you're going to get a sample mean that is lower than the population mean value, 99 or 97.5. There's no reason for your sample means to skew so that there are large, higher in value than the population mean. They're going to equally fall on one side or the other. So when you average across that, you're going to get exactly the population mean. And yeah, every once in a while, you're going to get an unusually high sample mean, like I had a sample mean of 104 or 105. That's not going to happen very often. It's going to happen once in a while. But you're just as likely, it's just as often going to happen that you're going to get a sample mean that is unusually low, like 96, something like that. And so again, they kind of add, when you average across all of them, you hit at the mean of the population. You can also compute the standard deviation, right? So we can treat these scores just like regular scores and compute the standard deviation. We know what the mean of the distribution is, right? You need that to compute the standard deviation. You need the mean of the distribution, right? The mean of the distribution is 100. So we can compute the standard deviation by taking each score, right? And again, we're treating the sample mean as a score, taking each score, subtracting the mean, right? We know how to do that. Take the deviation, square it, sum them all together, divide by n, and take the square root. Right? So theoretically, we could do that. Now it would tell us the standard deviation. What is the standard deviation? What's the definition of standard deviation? What does that tell you? It's the average amount the scores differ from the mean, right? The average amount scores differ from the mean. In the context of the distribution of sample means, it takes on a very important, unique meaning, right? So it still means the standard deviation still tells you on average how much the sample, right? In this case, the sample means the scores differ from the mean of 100, from its mean, whatever the mean is. In this case, it's 100. But that tells you something very interesting, because these aren't just regular scores, these are sample means from a population. And so the standard deviation is a kind of error, if you can think about it that way. It's the standard error, right? It tells you on average how much, any given sample mean should differ from the population mean. So it has the same meaning as a standard deviation, just like usual, but in the context of talking about sample means from the population mean, that's actually telling us, it's quantifying the amount of error that we expect. And so that standard deviation of the distribution of sample means, we actually give it a special name. We call it the standard error. So the standard deviation of the distribution of sample means is actually, we call it standard error, because it represents the average amount they would expect a sample mean to differ from the population mean. More generally, it's telling us the average amount to score differs from the mean of the distributions. It's the same definition, but in the context of sample means and the distribution of sample means, it quantifies the actual error you'd expect. Now I mentioned, we could compute the standard deviation, or in this case, a standard error, the way we learned how. Theoretically, we could do that. Again, we know the individual scores, and we know the mean of the distribution. It's equal, in this case, to 100. It's always going to equal to the population mean from which the samples were drawn. So we know that. So we can, like I said, you can subtract the mean from each of the scores, take the deviation, square it, sum them together, divide by n, and take the square root. But we don't need to know that. We don't actually have to do that because of the third special property of the distribution of sample means. And that is that the standard deviation, or in this case, the standard error, is a function of two things, and two things only. It's going to be important that you kind of understand what these are and why. So the standard error is equal to these two things. And you should actually know what those symbols are already. I'm going to introduce a new symbol. It's little sigma, but now it's got this what is that? Subtype next to it, right? A little X bar. Subscript, I guess is what it's called. So sigma with a little subscript, X bar. So that sigma is telling you that it's a standard deviation, which it is. But the X bar is telling you that it's a special type of standard deviation. In fact, it's the standard error. It represents the standard deviation of the distribution of sample means. So you want to learn that between now and Thursday. So the standard error tells us, on average, how much the scores, i.e. the samples, any given sample mean will differ from population mean. And it's a function of just two things. So n is the sample size. How large are your samples? That's going to affect the size of your standard error. The smaller your samples, instead of 50, I only had 10 people. I was taking just 10 people from the population where the mean was 100 and the standard deviation was 10. Well, just think about it. With just 10 people, it's very easy to get a sample mean that is just quite different from the population mean, right? It's easy to get one person who's really, really brilliant, and that's going to just throw off your entire sample mean very dramatically. If you have one person that's brilliant in a group of 50 or 100 or 200, that's not going to have as big of an impact as if you only have 10 people, right? So small samples are not very representative of the population. So it makes sense that that would be one of the two factors that affect the standard error. And in fact, this is a denominator. So The smaller it is, the smaller the denominator, right, the larger the value, right, the larger the value of the standard error. Right? So the smaller that n is, you're going to have a larger ratio. Okay, so one of the things that affects the standard error is the sample sizes. Right? The smaller your sample sizes, the greater the discrepancy you expect in your distribution of sample means, and the larger your standard error. Which is, if you think about what we're trying to do, is kind of bad. If I'm trying to figure out whether or not this 6-point discrepancy is actually due to my drug, the whole point of doing this is trying to be able to discount that as the cause of this 6-point difference. I want to be able to attribute that 6-point difference to something other than just sampling error that is represented by that distribution of sample means. And so if I expect there to be a lot of standard error, that's going to make it difficult to disprove or to show that that 6-point difference that I found in my study was due to something other than standard error. So we kind of, as researchers, to the extent that we can, we want to try and create a situation in which our sampling from that population is very precise. We're getting samples that are close to the population mean. And one way we can do that is to have larger samples. Okay, the second characteristic thing that affects our standard error is the standard deviation in the population. So that little sigma, that standard deviation, is a population parameter, so it's a population standard deviation. In this case, that was 10. So it's a measure of variability. How much do the scores in the general population vary? And in this case, if the individual scores in the population, if they vary a whole lot, that's going to increase the numerator. That's going to lead to a high standard error. And so if you increase the numerator value, that increases the ratio value. So the greater the individual scores, the greater the individual scores in the population vary, the greater your standard error, the more you expect your sample mean to be discrepant from the population mean, just based on standard error alone. Okay, and why is that? Why does the amount of individuals, how much the scores vary in the population, why does that affect how much error we expect between a sample mean and the population mean on average? And the only way I know how to describe this well is just to give an extreme example. Let's take an extreme example where the mean IQ is 100, because that's no different than what I've written up here. But in this case, let's say that there's no variance, there's no variability. Every single person has an IQ score of 100 in the population. So you've got 350 million people. Their IQ, each and every single person's IQ is 100. So of course, the mean of that population is going to be 100. Right? And the standard deviation is going to be equal to 0. There's no variability at all. All right, now let's think about taking a sample of 50 people from that population. Taking 50 people, just randomly selecting them from that population and computing the mean of that sample. Is that going to be any different from the mean of 100? It has to be 100, right? It has to be exactly 100, right? The only way you can have any discrepancy, the only way you can have any standard error is if there's at least a little bit of variability in the population. If there's no variability in the population, then you cannot get sample means that differ from the population mean. And then likewise, if you think about an extreme, the other situation where you have the scores all over the place. See how the mean is 100, but the standard deviation, say, is 50 or something, which is crazy, right? So the individual scores are all over the place. Well, in that case, it's quite easy to get a sample mean where you just happen to have a few people that have really, incredibly high scores that really fluctuate, right? So you need to have, the more fluctuation in the individual scores in your population, the larger the likelihood of getting a sample mean that also fluctuates quite a bit, because there's just more opportunity to get weird people, to get extremes in your sample that can make it one way or the other. And so for that reason, the standard deviation, the amount of variability that exists in the population, impacts our standard error. So the less variability there is in the scores in the population, the lower the standard error. Low standard error means that your sample means are expected to be pretty close to the population mean, just based on sampling error alone. Okay, well, we can actually figure out what the standard error is for this particular situation. Right, so the distribution of sample means, again, these are the kind of outcomes we'd expect just based on chance, just based on standard error, right? No effect on my drug. Again, this whole purpose of this is for that first part, right, where we're trying to figure out what kind of outcomes would we expect just based on sampling error, right? And in this case, it's the distribution of sample means where the mean of that distribution is 100 and the standard deviation or the standard error is equal to, we can figure that out. The standard deviation of the population is 10. And the sample size is 50. Kind of a small sample, not terribly small, but all right. And so then I can do my math. I'm going to cheat by looking at my paper. So 10 divided by the square root of 50 is equal to 1.41. And these are IQ points. All these numbers are something tangible. Right? So that mean of 100, that means 100 IQ points. That's the mean of of those particular sample means. Okay, so the standard error is 1.41. On average, we'd expect any one of these sample means to differ from the population mean or the mean of the distribution, which is equal to the population mean. We'd expect it to differ from 100 by 1.41 IQ points, by a little less than 1.5 IQ points. Right? So this particular sample means differs a little bit more than the average amount, right? Because it differs by 2 points rather than 1.41 point. Right? But again, that standard error is again the standard. It's the average amount. The sample means differ from the population mean. This one only differs by 1 point, right? That one only by 0.5. This one by 2.5, right? So again, that standard error again is the average. It's overall what is expected. Right? And any given sample mean, would likely not be that exactly. We can flesh this out a little bit now too. So this is the distribution of sample means that I have written on page 1. So you can see those numbers are along the baseline now. So one standard deviation above is 1.1.41. 2 standard deviations above is 102.82. 3 standard deviations above is 104.23. 1 standard deviation below is 98.59. 2 standard deviations below, or I could say standard errors below, is 97.18, and I could keep going. And I can actually put the z-score equivalents right below that. We know how to do that. Okay, the z-score of any distribution, the mean of any distribution is equal to a z-score of 0. So I anchor it there, start that, and that's 1, 2, 3. So I can put the corresponding z-scores here. Okay, so that corresponds to that first main step. What kind of outcomes would I expect based on sampling error alone? And it's because we know quite a bit about the distribution of sample means that we can kind of picture that. We don't actually literally have to do this, or we don't have to take a random sample of 50 individuals and do that an infinite number of times. And the reason for that is because of the properties that are known of the distribution of sample means. Okay, we know that it's normally distributed as long as your sample sizes are above 29. We know that the mean of the distribution of sample means is equal to the population mean from which they were drawn. And we know that the standard error is a function of the standard deviation of the population and the sample size. And with that information, we can get a real grasp on what kind of outcomes we'd expect based on chance. Okay, 2 things. One, there is a website that I have underlined down at the bottom of that page. And I always want to, but I kind of run out of time. And you can always go there yourself, because one of the questions people have is, how do you know that this is true? How do you know that the standard error, for example, is equal to the standard deviation divided by the square root of n? And there's a couple of things that you can do. One is you can actually try and do it yourself. by making up your own population. You can have like 6 numbers, right? Just take 6 numbers and then sample 2 at a time and do it. You can't do it an infinite number of times, but you can do it like 100 times. I can give you kind of a good picture. And you can actually, take 100 samples. So you have 6 numbers. Just take pieces of paper, 1, 2, 3, 4, 5, 6. And then just take a repeated number of 2, just randomly select 2 at a time and compute the mean of any 2 numbers. So you can actually come up with that. 100 or 200 should be enough. And then you can see that the distribution will be approximately normal in shape. It won't be exact because you're not going to do it until you get a finite number of random samples. But and then you can compute the mean, and you'll see that it'll be very close to the mean in this case, which is, I believe, 3, the mean of the population. You can compute the standard error by taking the 100 or 200 samples they have computed. You have their sample means, and then subtract the mean to square those deviations, sum them together, and you can see that the standard deviation is equal to the same thing you get if you use that formula. Now, that's a lot of work and not much fun. The website down there shows a simulation of the exact same thing. So you can, in a split second, you can take 300, 400, 500 samples, and you can do that. And maybe I'll have time to do that in class one day, we'll see. Okay, all right. So that's the one thing I wanted to mention about that. Secondly, well, now we have some insight. Now we have some context with which to understand my sample mean of 106, right? Okay, so I did a study. I took 50 people from that population. I randomly selected them from that population. I gave them my drug for 6 months. I wanted to see if it impacted IQ. I got a sample mean of 106 from those people. And so my question is, that 6-point difference, do I have reason to suspect that that's actually due to my drug? Because I cannot just instantly conclude that because of sampling error. Well, that's where we come to that second part of this process, right? The first part was to figure out what kind of outcomes we would expect based on sampling error. The second part was to take our particular outcome and compare it to what would be expected by chance. 106, where would 106 fall, right? These are the outcomes, quite literally, the outcomes that we would expect by sampling error alone. 100, one standard error above is 101.41, 102.82 is 2 standard errors, 3 standard errors, still not there. Here's another one, 105. Point what? 105, and I have to add what? 41, 4, 6, 3. 4 standard deviations, a z-score of 4. Still not at my mean of 106. My mean is right up here. It's beyond 4 standard errors or 4 standard deviations above the mean. Did my drug likely have an effect? These are the kind of outcomes I'd expect based on sampling error alone. Likely, yes, yeah. So 2 really important points. One is, yes, it's exceedingly unlikely that my sample mean of 106 was just due to sampling error. I.e., there's very likely a real effect going on here, right? Because I can show in the context of what kind of outcomes we would actually expect based solely on sampling error. My sample mean is way up here. It is very likely, it's very unlikely to have occurred just by sampling error alone. And that is really what we're going to do for almost the entire rest of the semester, is engage in this process. Figure out what kind of outcomes we'd expect based on sampling error alone. Then we take our particular outcome, see where it fits in there. If my sample mean was 102, it wasn't, but if it was, well, that's pretty likely to have occurred by sampling error alone, right? So in that case, I wouldn't have any evidence, really, that my, 100, yeah, my mean was 102, that's higher than the population mean, but that's not that discrepant. That's kind of falls into the realm of what we'd expect based on sampling error. But a sample mean of 106, that is very unlikely, right? Whenever you fall into one of the tails, it's really unlikely to have occurred by sampling error alone. And so in those cases where our outcome does not fit in with what you'd expect based on sampling error alone, that's when we have evidence it's something other than sampling error that is driving the effect, i.e. that there's a real effect of your manipulation, in this case, the drug. And this is going to be a lot more to it, exactly where do you draw the line, where do you decide whether there's an effect or not. So we're going to get into those trees later in the semester, probably on Thursday. But that's the process. Okay. Another thing to point out, and this is true of all inferential tests, our conclusions are probabilistic. It is very unlikely that this 6-point difference was just sampling error. It's very likely that the drug has an effect. Right? And I am justified in claiming that there is an effect of my drug, given that I was able to sufficiently rule out sampling error. But I wasn't able to rule it out completely. I can sufficiently rule it out, but there's a possibility that I would get a sample mean of 106. There's a possibility I'd get a sample mean of 130. It's very unlikely, but if you take an infinite number of samples from the population, eventually you're going to get a sample mean of 130, right? 1 out of, 80 trillion or something like that. So that there's, whenever you get an outcome, you cannot definitively prove it was due to your drug. And that's one reason why, and it really infuriates a lot of people, one reason why scientists are always very hedgy, or they don't use the word prove, right? If you look at the actual articles that they write, they don't use the word prove. They say support. They say, they use words like that. So the conclusions that are drawn are probabilistic. That being said, when scientists find the same result over and over and over again, that's where we get confidence. So typically a researcher, they get one result and they conclude that there's an effect. It's at that point still tentative. Right? It's only when you find the result over and over again where you're able to, find that the outcome of that drug, one study after another, is really discrepant from what you'd expect by sample error alone. It's only at that point that we really embrace the finding. Right? And that's another thing that really frustrates a lot of people because, a research finding comes out showing that there's an effect of, caffeine on something, right? But it's really just one study. And unfortunately, a lot of people like to read about their health and read about psychology. And so when there's a study that's published, a lot of times the popular press will pick up on it and then publish it, right? Because people like to read it. And if I had my way, it wouldn't actually be published, widely dispersed until it's been replicated a few times. But so that's why sometimes you read a finding, caffeine has this effect on Alzheimer's. And then, 3 years later, you find that it doesn't, right? And you're like, oh, what's science is bad. But it's really that, unfortunately, that information gets out before there's a definitive, strong basis with which to make that conclusion. Okay, on Thursday, we're going to take a situation like this. We're going to kind of break it down and learn about the systematic steps that are involved in doing all of this. So this is kind of like the forest type of coverage of inferential statistics. And then on Thursday, we're going to start, learning, what are their criteria, what do we know, and we can make a conclusion that there's an effect or not, and so on.